What would happen if humanity were permanently confined within the Milky Way by insurmountable physical barriers? The immense distances between galaxies combined with the ever-accelerating expansion of space-time render any attempt to leave the Milky Way futile from the very moment of departure. The laws of Einstein's relativity impose an absolute ceiling. Reaching the speed of light would require infinite energy, while approaching it would trigger severe consequences such as extreme time dilation, biological degradation of the human body, and the complete breakdown of radio communication between a spacecraft and Earth. Faced with this reality, humanity should not view this galactic prison as a sentence, but as a magnificent home, a vast cosmic ecosystem with nearly limitless potential for exploration. Rather than pursuing science fiction fantasies that lie beyond the reach of physical law, humanity should focus on building a sustainable, profound, and enduring civilization within the Milky Way, which is already vast enough to contain our ambitions for billions of years. In what follows, we will explore the fundamental limits humanity faces within the Milky Way and the time paradoxes introduced by relativistic physics. There exists a specific number in astrophysics that most researchers prefer to gloss over during press conferences on space exploration, a figure so devastatingly large that when truly comprehended, it collapses the fantasy of an intergalactic civilization like a house of cards. That number is 2.5 million light-years. This is the abyss separating us from Andromeda, our nearest major galactic neighbour. To the uninitiated, light-years are just abstract units. But to understand why we are imprisoned, we must translate this into a physical scale our primate brains can process. If we were to shrink the Milky Way, a colossal structure containing hundreds of billions of stars, down to the size of a standard €1 coin held in the palm of your hand, Andromeda would be another coin floating nearly 3 meters away. On this scale, the distance seems deceptively manageable, perhaps a few steps across a room. But this model hides a terrifying reality: the scale of our progress within that coin. Consider Voyager 1, the fastest and most distant object ever built by human hands. It has been screaming through the void for 47 years at speeds exceeding 60,000 kilometers per hour. Yet in the context of our galactic coin, Voyager has not even travelled the width of a single bacterium. It has barely scratched the surface of our own solar neighbourhood. If we pointed Voyager 1 directly at Proxima Centauri, the absolute nearest star to us, it would take 73,000 years to arrive. That is a span of time 10 times longer than recorded human history. Now apply that same velocity to the gap between galaxies. With our current premier technology, crossing the emptiness to Andromeda would require approximately 1.8 billion years. By the time a human spacecraft arrived, Earth's oceans would have likely boiled away due to the sun's increasing luminosity, and humanity would be a fossil record long ground into dust. We are not merely slow, we are effectively stationary. However, the tragedy is not just about the time it takes to cross the distance, it is about the nature of the nothingness we must survive. The sheer distance is paralysing, but the true nightmare lies in the nature of the terrain we must cross. In our scale model, where the Milky Way is a coin, every single millimetre of the dark gap separating us from Andromeda represents 1,000 light-years of frozen lethal emptiness. When we say empty space in the context of our solar system, we are being imprecise. The space between planets is relatively cluttered with solar wind dust and debris. But the space between galaxies, the intergalactic medium, is a void of a completely different order. It is an abyss of such terrifying purity that it defies terrestrial logic. Here the density of matter plummets to roughly 1 atom per cubic metre, and in the vastest voids perhaps 1 atom per several cubic meters. To put that in perspective, the best vacuums created in our most advanced laboratories on Earth are thick, choking fogs compared to the sterile clarity of the intergalactic deep. Imagine a journey where you look out the viewport for 10,000 generations and see absolutely nothing. No stars, no planets, not even a mote of dust or a stray hydrogen atom to break the monotony. It is a sensory deprivation tank the size of a universe, and it is cold, a stillness settled at 2.7 Kelvin, just a breath above absolute zero, representing the fading residual heat of the Big Bang itself. This is not merely a lack of features, it is a thermodynamic desert designed to strip energy from any object foolish enough to enter it. It is a perfect sterile silence that has endured for billions of years, a dark ocean that does not want to be sailed, effectively quarantining the islands of light where life is permitted to exist. Before we can even discuss the time it takes to cross this void, we must confront the price the universe charges for the attempt energy. Having confronted the scale of the void, we naturally turn to the solution speed. If the distance is too great, we must simply travel faster. But this is where the universe reveals its most formidable defense mechanism, a barrier not made of matter, but of energy. This barrier is guarded by the laws of thermodynamics, and they are not laws that can be broken. They are the absolute terms of our existence. To understand the magnitude of the problem, let us strip away the science fiction fantasy of weightless starships and look at the brutal requirements of moving mass. Consider a modest vessel weighing approximately 1,000 tons, roughly the mass of the International Space Station. To make an intergalactic journey viable within a civilization's memory, we might aim for 50% of the speed of light. At this speed, a trip to Andromeda would still take 5 million years, but let us accept that as a starting point. The energy required to accelerate this single modest ship to half the speed of light is approximately 1,300,000,000 terajoules. To put that number into a human perspective, if you combined every joule of electricity generated by every power plant nuclear reactor, solar panel, and wind turbine in human history from the Industrial Revolution to the present day, it would not be enough. We would need to burn the entire energy output of our civilization for decades just to launch one ship. And that is only for the outbound acceleration. To stop at the destination, you must expend exactly that same astronomical amount of energy again to decelerate. But 50% of light speed is too slow. To reach Andromeda in a human lifetime, we need to go faster, approaching 99% of the speed of light or more. Here we collide with the thermodynamic usurer, the relativistic kinetic energy equation. In our daily lives, we're used to Newtonian physics where doubling your speed requires 4 times the energy. It is a fair trade. But as you approach the speed of light, the universe changes the exchange rate. The equation shifts from the simple Newtonian half-mass velocity squared to a relativistic monster involving the Lorentz factor. As you push closer to the speed of light, the energy required does not just increase, it explodes exponentially. To reach 90% of light speed requires double the energy of 50%. To reach 99% requires 10 times more. By the time you aim for 99.99%, the speed necessary to make the trip feel like a few years for the crew, the energy demands become literally infinite. The universe demands more energy than exists in entire stars just to push a few extra meters per second. And how do we carry this energy? This brings us to the tyranny of the Tsiolkovsky rocket equation. To accelerate, you need fuel, but that fuel has mass, so you need more fuel to accelerate the fuel you are carrying. This creates a vicious, self-defeating spiral. For an intergalactic mission, the math suggests a fuel-to-payload ratio of roughly 1 million to 1. For every single kilogram of ship crew or scientific instrument, you would need to launch with 1 million kilograms of fuel. We are not building a ship. We are building a flying mountain of volatile propellant teetering on the edge of physics, trying to pay a debt to thermodynamics that can never truly be settled. Faced with the crushing tyranny of the rocket equation, science fiction authors and futurists often play their trump card antimatter. On paper, it appears to be the salvation of interstellar travel, the perfect fuel that could cheat the thermodynamic limits of chemical propulsion. The logic is seductive because the physics behind it is undeniably elegant. When a particle of matter meets a particle of antimatter, they do not merely burn, they annihilate. They undergo a complete conversion of mass into energy, governed by Einstein's famous equation E equals mc squared. In this reaction, the efficiency is 100%. Every single proton and neutron is transformed into pure blinding radiation. Theoretically, a single gram of antimatter reacting with a gram of normal matter releases nearly 90 petajoules of energy, more than the atomic bomb dropped on Hiroshima contained in a thimble. It seems like the key to unlocking the galaxy. However, this promise is a mirage that evaporates the moment we confront the logistics of production. The fundamental problem is that antimatter is not a fuel source that we can mine or harvest. It does not exist in nature in any usable quantity. It must be manufactured. And here the laws of thermodynamics strike back with vengeance. To create antimatter, we must concentrate immense amounts of energy into particle accelerators to rip pairs of matter and antimatter out of the vacuum. This process is horrifically inefficient. We must put in far more energy to create the fuel than the fuel will ever release upon annihilation. It is analogous to filling a car's gas tank by burning 10 gallons of gasoline to synthesize a single gallon of superior fuel. The net energy balance is zero, or in practice profoundly negative. Let us look at the production capabilities of our civilization's crowning scientific achievement, CERN. In its most productive runs, the particle accelerator can generate approximately 10 million antiprotons per minute. This sounds impressive until you do the math. At this maximum production rate, running the facility continuously without pause or failure, it would take approximately 100 million years to produce a single gram of antihydrogen. We need thousands of tons for an intergalactic vessel, yet we would need geological epochs just to fuel a model rocket. Even if we could magically conjure this fuel, we face the nightmare of containment. Antimatter cannot touch any physical substance, not a wall, not a container, not an atom of air, or it detonates instantly. We must suspend it in absolute vacuum using powerful magnetic fields known as Penning traps. These traps require a constant fail-safe power supply. A single power outage, a single magnetic fluctuation, or a microscopic meteoroid breach would not just disable the ship. It would trigger a reaction equivalent to a thermonuclear warhead, vaporizing the vessel instantly. Antimatter is not a solution. It is a volatile battery that takes eons to charge and threatens to kill its users at every second. Let us indulge in a moment of supreme optimism. Let us assume that we have somehow conquered the thermodynamic wall. Imagine we have solved the energy crisis, built a magical engine that requires no mass, and can accelerate a vessel to 99.99% of the speed of light. We launch our brave explorers toward Andromeda. They are travelling fast enough to bridge the abyss in their own lifetimes. But in doing so, they have not defeated the universe. They have merely walked into its most insidious trap, the manipulation of time itself. This trap is governed by the Lorentz factor, represented by the Greek letter gamma gamma. It is the mathematical dictator that determines how time flows for a moving object relative to a stationary one. At terrestrial speeds, driving a car or flying a jet, the factor is effectively once, meaning time is shared equally. But as you approach the speed barrier, the factor spikes asymptotically. At 99.99% of the speed of light, the Lorentz factor is approximately 70. This means that for every single year that passes for the crew inside the ship, 70 years pass back on Earth. This phenomenon often trivialized in high school physics problems, as the twin paradox becomes a source of existential horror at intergalactic scales. The crew is not merely travelling through space, they are encased in the amber trap. Like an insect preserved in hardened resin, they are frozen in a state of near immortality relative to the outside world. To the explorers, the journey to Andromeda might feel like a manageable voyage of a few decades. They live, they work, they age slightly. But outside their hull, the universe is fast-forwarding at a terrifying rate. Consider the arithmetic of a return journey. The crew travels to Andromeda, spends a few years exploring and returns. For them, perhaps 60 or 70 years have elapsed a single human lifetime, dedicated to the greatest expedition in history. But because Andromeda is 2.5 million light-years away, the timeline on Earth has advanced by 5 million years. When the ship decelerates back into the Milky Way, the crew does not return home. They return to a planet that has effectively become an alien world. In 5 million years, tectonic plates will have shifted the continents into unrecognizable shapes. The climate will be radically different. The languages, cultures, and nations they knew will have dissolved into dust eons ago. Even the human species itself will likely have evolved into something completely unrecognizable or gone extinct entirely. The travellers become historical ghosts, living anachronisms ejected from their own era. They are severed from every person they ever loved, every institution that funded them, and every context that gave their mission meaning. They are orphans of time, drifting in a vessel that is less a ship and more a time capsule from a forgotten age. The universe allows you to travel to the stars, but the price of the ticket is everything you leave behind. And while the crew deals with this temporal isolation, they face an even more immediate problem. During the voyage, they are screaming into a void that refuses to carry their voice. As the travellers drift through the temporal amber encased in their high-velocity preservation, they face a second equally suffocating isolation, the death of their voice. We often take communication for granted, assuming that as long as we have a transmitter, we can send a message back home. We imagine the delay will be the only problem, waiting 2.5 million years for a signal to reach Earth, but the reality is far more brutal. At intergalactic scales and relativistic speeds, the connection is not just delayed, it is physically severed. The first executioner of communication is the inverse square law. Radio signals or even laser pulses do not travel in perfectly straight lines forever. They spread out as they travel. The intensity of the signal diminishes by the square of the distance. By the time a signal travels the 2.5 million light-years from Andromeda to Earth, it has spread so thin that its energy is virtually indistinguishable from the background noise of the cosmos. To send a simple hello that could be detected by our most powerful radio telescopes today, the spacecraft would need a transmitter antenna the size of a planet broadcasting with the power output of a small star. A standard shipboard antenna would be whispering into a hurricane. But the situation worsens when we factor in the ship's velocity. Because the vessel is travelling away from Earth at 99% of the speed of light, any signal it sends backwards suffers from an extreme Doppler shift. Just as a siren's pitch drops as an ambulance drives away, the light and radio waves from the ship are stretched violently. A message transmitted in the energetic X-ray or visible light spectrum would arrive at Earth stretched into ultra-low frequency radio waves, long lethargic undulations that carry almost zero energy and are nearly impossible to detect against the static of the universe. Furthermore, there is a phenomenon known as relativistic beaming. As an object approaches light speed, the radiation it emits is concentrated in the direction of travel like the beam of a headlight. The ship blasts blinding radiation forward toward Andromeda, but behind it toward Earth, it falls into a deep relativistic shadow. The signal strength radiating backward drops precipitously. This creates a terrifying paradox. To reach the stars, you must go fast, but if you go fast enough to get there, you become mute. The crew would be screaming into the void, but the physics of their own velocity would stifle their cries before they even left the ship's wake. There is no mission control, no updates, no farewells. There is only the ship, the void, and a silence so absolute that it erases the existence of the traveller long before the mission ends. And while the ship falls silent, the universe itself is busy ensuring that the destination they are chasing remains forever out of reach. While our hypothetical travellers are frozen in time and silenced by physics, the universe around them is engaging in a final devastating act of betrayal. We tend to think of space as a static stage, a fixed empty container through which stars and galaxies move. But this model is fundamentally wrong. The stage itself is active dynamic and actively hostile to the concept of travel. Space is not merely distance. It is a substance that is constantly being created, stretching the gap between us and our destinations every single second. This phenomenon is codified in the Hubble-Lemaitre law, a rule that transformed our understanding of the cosmos from a static painting into a terrifyingly dynamic prison. The law states that the universe is expanding, and it does so at a specific rate, approximately 70 kilometers per second, for every megaparsec, 3.26 million light-years of distance. This sounds abstract, but its implications for travel are catastrophic. It means we are trapped on a cosmic treadmill. Imagine trying to swim toward a distant shore. In a static ocean, your progress is simple, every stroke brings you closer. But in our universe, the ocean itself is expanding. For every meter you swim forward, the water creates new distance between you and the land. You're chasing a receding shore. If the shore is close enough, you can swim faster than the expansion and eventually arrive. This is the case with Andromeda. At 2.5 million light-years, the mutual gravity between our Milky Way and Andromeda is strong enough to overpower the expansion, pulling us together at 110 kilometers per second. We are the lucky exception, a local cluster bound by gravity. However, once we look beyond our immediate neighbourhood, beyond the local group, gravity loses its grip and the expansion takes over completely. Consider a galaxy just outside our cluster, perhaps 300 million light-years away. The space between us and it is expanding so rapidly that the galaxy is being carried away at hundreds of kilometers per second. If you aim a ship at it, you're not just fighting the initial distance, you're fighting the new space being born in front of your nose. This creates a race condition that physics guarantees we will eventually lose. As we look deeper into the cosmos, the cumulative effect of this expansion accelerates. At a distance of approximately 14 billion light-years, the recession velocity of galaxies hits a critical threshold, the speed of light. At this point, the galaxies are receding from us at 300,000 kilometers per second. This does not violate Einstein's relativity, because the galaxies are not moving through space faster than light. The space between us is swelling at that rate. For the intergalactic traveller, this is the ultimate futility. You could build a ship that travels at the speed of light, the absolute maximum speed limit of the universe, and you would still be running in place. You would never get any closer to your target. You would be running at full speed on a treadmill that matches your pace exactly, while the destination remains a fixed, mocking mirage on the horizon. And beyond a certain point, the treadmill moves faster than you can ever run, pushing the destination backward into the darkness, no matter how long you travel. The mechanics of the cosmic treadmill lead us to a terrifying demarcation line in space, a boundary as absolute as the edge of a cliff. Astronomers call this the cosmic event horizon. It represents the point of no return, the precise distance where the speed of space's expansion equals the speed of light. Any event happening beyond this line, any signal sent, any light emitted, any ship launched, is irrevocably disconnected from us. The information simply cannot swim upstream against the current of expanding space fast enough to ever reach Earth. We are accustomed to seeing images of the observable universe, a grand sphere containing approximately 2 trillion galaxies. But this map is a deception. It is a map of the past, not the present. We see these distant galaxies not as they are now, but as they were billions of years ago, when the light we are receiving today first began its journey. In the intervening eons, while that light was travelling, the space between us and them has swelled efficiently and relentlessly. The brutal reality, confirmed by calculations from the California Institute of Technology, is that the vast majority of these galaxies have already crossed the horizon of reachability. Specifically, any galaxy currently situated beyond approximately 4.6 billion light-years is moving away from us faster than light can chase it. Even if we could leave today at light speed, we would never catch them. This leads to a statistic that induces a form of cosmic vertigo. Approximately 94% of the galaxies in the observable universe are already permanently beyond our reach. They are visible to us only as ghosts, images of a time before they were carried over the edge of the abyss. We can see them, we can name them, and we can study them, but we can never ever touch them. They are effectively deleted from our future, severed from our causal timeline by the geometry of the universe itself. Worse still, this prison is shrinking. The expansion of the universe is not constant. It is accelerating, driven by the mysterious force known as dark energy. This acceleration means that the reachability horizon is contracting over cosmic time. Galaxies that are theoretically reachable today, hovering just on the edge of our grasp, will be pushed over the horizon tomorrow. In 1 billion years, thousands more galaxies will slip past the point of no return. We are living in a unique, fleeting moment in cosmic history, where we can see the full glory of the cosmos yet are powerless to engage with it. If we look far enough into the future, approximately 100 billion years, this acceleration will sweep away every galaxy outside our local group. They will fade into the redshifted darkness and disappear completely. Future astronomers born in that era will look up at a sky that is black and empty, save for the few stars of our own merged galaxy. They will have no way of knowing that a wider universe ever existed. We are witnessing the slow, irrevocable closing of the cosmic shutter, sealing us inside our local island of matter, while the rest of creation vanishes into a void of absolute finality. We have spent much of this analysis discussing the limits of engineering energy and space-time geometry. But even if we could build a ship that defies the rocket equation, navigates the expanding universe, and maintains communication across the void, there remains a final, non-negotiable component of the mission: the cargo. That cargo is us. And this brings us to the most intimate barrier of all. We are not beings of the void. We are biological organisms evolved specifically for the surface of a rock, orbiting a G-type star protected by a thick atmospheric blanket and a geodynamo-generated magnetic shield. When we strip away these layers of protection and venture into the intergalactic abyss, the human body ceases to be an explorer and becomes a decaying biological artifact. The primary executioner in deep space is radiation, but not the kind we typically fear on Earth. Here we worry about UV rays or minor radioactive leaks. In space, the threat is particulate. Inside the solar system, we are bathed in the solar wind, but we're also protected by the sun's heliosphere, a magnetic bubble that deflects the worst of the high-energy particles coming from the galaxy. However, once a ship crosses into the intergalactic medium, it loses even that tenuous protection. The vessel is exposed to the full, unfiltered fury of galactic cosmic rays, GCRs. These are not rays of light. They are subatomic shrapnel, mostly protons and heavy atomic nuclei, accelerated by supernova explosions and black holes to nearly the speed of light. They carry so much kinetic energy that they do not merely burn tissue, they tear through it on a molecular level. When a GCR strikes a human cell, it acts like a microscopic bullet. It can shatter the sugar phosphate backbone of our DNA, causing double-strand breaks that are notoriously difficult for cellular machinery to repair. In the intergalactic void, this bombardment is constant and omnidirectional. It creates a sterilizing rain that penetrates the hull of the ship. The clinical reality is grim. The cumulative dose over a voyage of centuries would not just increase the risk of cancer, it would systematically dismantle the crew's central nervous systems, degrade cognitive function, and liquefy bone marrow. The engineering solution seems obvious shielding. We could surround the crew quarters with thick layers of water polyethylene or lead to absorb the impact. But here the thermodynamic usurer returns to haunt us. To effectively block high-energy GCRs, you need meters of shielding material. This adds thousands of tons of dead mass to the ship. As we established with the rocket equation, adding mass requires exponentially more energy to accelerate, which requires more fuel, which adds more mass. Some have proposed active shielding, generating massive magnetic fields around the ship to deflect the particles mimicking Earth's magnetosphere. However, to deflect relativistic protons, the magnetic field would need to be immense, extending for kilometers around the vessel, requiring a continuous power supply that rivals the output of a commercial nuclear reactor. And even then, it would not stop neutral particles like high-energy neutrons or gamma rays, which pass through magnetic fields as if they were ghosts. We are left with a stark physiological conclusion: the human body is too fragile for the environment it seeks to conquer. We are soft water-filled sacks of chemistry, trying to survive in a nuclear furnace. Since a single human lifespan is laughably insufficient to cross the void, and cryonic suspension remains a gamble, with cellular integrity proponents of interstellar colonization pivot to the concept of the generation ship. The logic is biblical in scale. We build a flying ark, a self-sustaining world where the crew lives, reproduces and dies, passing the torch of the mission to their children. The generation that arrives at the destination will be the great-great-grandchildren of the generation that launched. But this solution merely trades a biological problem for a sociological nightmare. The first hurdle is purely genetic. You cannot populate a new world with a skeleton crew. To avoid inbreeding depression, the accumulation of harmful genetic mutations that occurs in small populations, you need a substantial gene pool. While early estimates suggested the 50-500 rule, 50 individuals to prevent inbreeding, 500 to maintain genetic drift, modern analyses suggest a minimum viable population MVP of anywhere from several thousand to 40,000 individuals to ensure long-term health over millennia. This is not a spaceship, it is a flying city, and this city must be a closed loop where absolutely nothing is lost. Every drop of water, every breath of oxygen, and every gram of carbon must be recycled with 100% efficiency forever. The historical precedent for such closed-loop systems is discouraging. The most ambitious attempt on Earth Biosphere 2 collapsed in less than 2 years, with only 8 inhabitants. Oxygen levels plummeted, pollinators died, and social factions emerged. Now imagine scaling that complexity to support thousands of people, not for 2 years, but for millions of years. In the closed thermodynamic system of a ship, entropy is relentless. A single failure in the water filtration cycle, or a blight on the hydroponic crop, spells extinction for the entire colony. But the generation trap is most devastating on a psychological level. The intermediate generations, those born in the void, are born into a prison they did not choose. They will never walk on solid ground, never feel rain, and never see a horizon that isn't a metal bulkhead. They exist solely as reproductive vessels for the ambition of ancestors they never knew, destined to die, in transit to a paradise they will never see. What happens when the 3rd or 4th generation questions the mission? Why should they sacrifice their lives maintaining a ship for a destination that is merely a myth to them? The likelihood of mutiny, social collapse, or a fundamental shift in ideology is a near certainty over deep time. Finally, there is the silent work of evolution. Natural selection does not stop because we have left Earth. Over thousands of generations in a high-radiation, low-gravity artificial environment, the crew will adapt. Their bodies will change to suit the ship, not the planet, at the end of the journey. By the time the vessel arrives at Andromeda, the beings disembarking may no longer be biologically human. They would be a new species evolved for the void, likely incapable of surviving on the open surface of the world they came to conquer. The mission succeeds, but humanity as we define it fails to arrive. When the human mind is cornered by the undeniable brutality of the rocket equation and the suffocating limits of biology, it instinctively retreats into the sanctuary of science fiction. For nearly a century, our cultural narrative has been dominated by a convenient mythology, the belief that the laws of physics are merely suggestions, obstacles that can be bypassed with sufficient cleverness and future technology. We invoke terms like warp drive, wormholes, and hyperspace, not as scientific theories but as magical incantations designed to ward off the despair of isolation. However, when we strip away the narrative armour and subject these concepts to the cold scrutiny of general relativity and quantum field theory, they do not offer an escape. Instead, they reveal new and even more impassable walls. Let us begin with the most seductive of these concepts, the Alcubierre warp drive. Proposed by physicist Miguel Alcubierre in 1994, this idea suggests that instead of moving the ship through space, we could move the space around the ship. By contracting the fabric of spacetime in front of the vessel and expanding it behind the ship would ride a wave of distorted geometry, technically remaining stationary inside a bubble, while moving faster than light relative to the outside world. On the surface, it appears to be a brilliant loophole in Einstein's prohibition against faster-than-light travel. However, the mathematics of the Alcubierre metric contains a poison pill. To create the necessary distortion of space-time, the equations demand a form of energy density that is strictly negative. This is not antimatter, which has positive mass and positive energy. This is exotic matter, with negative mass material that weighs less than nothing, exerts negative pressure and produces repulsive gravity. While quantum mechanics allows for fleeting microscopic instances of negative energy density such as the Casimir effect, where two plates placed nanometers apart exclude certain vacuum fluctuations, scaling this up to a macroscopic level is a problem of a different order. To construct a warp bubble large enough to encompass a modest spacecraft, early calculations suggested we would need a mass of negative energy equivalent to the entire planet Jupiter. Even with refined modern geometries, the energy requirements remain astronomical. We're talking about converting the mass of entire celestial bodies into a substance that may not fundamentally exist in stable, macroscopic quantities. Furthermore, even if we could conjure this impossible fuel, the warp drive suffers from a fatal control problem. The horizon of the warp bubble, the front edge where space is being compressed, is causally disconnected from the interior. The crew inside the ship cannot send a signal ahead of them to tell the bubble to stop or turn, because that signal would have to travel faster than the bubble, which is already moving faster than light. The ship would be a prisoner of its own velocity, unable to steer, unable to brake, ploughing through the universe in a blind, uncontrollable straight line until it ran out of energy or obliterated a star system. If we cannot warp space, the next desperate hope is to fold it the Einstein-Rosen bridge or wormhole. The concept is to create a tunnel through the bulk of space-time connecting two distant points, like a handle on a coffee cup. Again, general relativity permits these structures mathematically, but the universe appears to loathe them physically. A natural wormhole, if one were to form, is inherently unstable. The moment a single photon or particle of matter attempts to enter the throat of the wormhole, the gravitational stress triggers a feedback loop that causes the tunnel to pinch off and collapse. The collapse happens so instantaneously that not even light can cross the gap before the bridge is severed. To keep the throat open, we return to the same impossible requirement. As the warp drive, we must thread the wormhole with vast quantities of negative energy to provide the repulsive force needed to counteract the crushing gravity of the collapse. But let us assume we solved the stability problem. We are still left with the logistical nightmare of placement. Wormholes do not simply appear where we want them. To create a bridge between Earth and Andromeda, we would first have to construct one end of the wormhole here and then physically tow the other end to the destination. Since we cannot travel faster than light to deliver the exit, the initial setup of the transportation network would still take millions of years. We would have to travel the slow, hard way to build the shortcut. The wormhole is not a tool for exploration. It is at best a highway for a civilization that has already conquered the distance by conventional means. Finally, we must address the most profound barrier of all causality. In the geometry of our universe, space and time are woven into a single fabric. The speed of light is not just a speed limit for movement, it is the speed of causality, the maximum speed at which an effect can follow a cause. If you succeed in building a machine that allows you to travel faster than light purely by the geometry of the Lorentz transformation, you have inherently built a time machine. There are valid frames of reference in which a faster-than-light traveller arrives at their destination before they departed. This opens the door to logical paradoxes that shatter the coherence of reality, the ability to send a message back in time to prevent your own birth or to stop the mission from ever launching. Most physicists subscribe to the chronology protection conjecture, which suggests that the laws of physics effectively conspire to prevent the formation of closed time-like curves. The universe creates instabilities, vacuum fluctuations, radiation spikes, or energy divergences that destroy any mechanism attempting to violate causality. Other exotic solutions, such as tapping into the zero-point energy of the quantum vacuum, fail for thermodynamic reasons. The quantum vacuum is the ground state, the lowest possible energy level of a system. Trying to extract usable work from the vacuum is like trying to drain water from a lake that is already at its absolute lowest depth. There is nowhere for the energy to flow. When we look at the sum of these obstacles, a stark picture emerges. The speed of light is not a technical hurdle like the sound barrier waiting to be broken by a better engine. It is the fundamental pixel size of the universe, the conversion rate between matter and energy, and the synchronization signal of time itself. The escape hatches of science fiction are mathematical curiosities, not engineering blueprints. The universe has locked the doors, and it has thrown away the key not out of malice, but because the structural integrity of reality depends on those doors remaining closed. We are not going to warp speed. We are not jumping through hyperspace. We are staying here bound by the rigid, beautiful and absolute laws of the Milky Way. The realization that the intergalactic abyss is effectively impassable strikes a devastating blow to the human ego, which has been nurtured on stories of infinite expansion. We feel trapped, claustrophobic, as if the universe has pulled the rug out from under our destiny. But this despair is born of a failure of perspective, not lack of resources. If we stop staring longingly at the locked doors of the cosmos and turn around to examine the room we are in, we discover that our prison is actually a fortress of unimaginable abundance. The Milky Way is not a tiny cell, it is a sprawling island universe. It contains approximately 400 billion stars. Orbiting these suns are at least 100 billion planets. Even by conservative estimates, there are 20 billion Earth-sized worlds resting in the habitable zones of their parent stars. To call this a limitation is absurd. If humanity were to colonize one new solar system every single day, it would take us over 1 billion years just to visit every address in our own zip code. We do not need to cross the void to find infinity. We have enough matter and energy right here to occupy our species for eons. In terms of the Kardashev scale, a method of measuring a civilization's technological advancement based on energy consumption, humanity is currently not even a Type 1 civilization. We barely control the resources of our own planet. The Milky Way offers us the potential to become a mature Type 2, or even a Type 2 civilization. We have the raw materials to construct Dyson swarms around millions of stars, harvesting every photon of energy to power megastructures the size of solar systems. The prohibition against intergalactic travel forces us to adopt a sanctuary strategy. Instead of acting like locusts looking for the next field to consume, we must become gardeners of the galaxy we inhabit. We are not prisoners. We are the inheritors of a kingdom so vast that its boundaries are practically irrelevant to our daily existence. The physics that traps us here also protects us, enforcing a quarantine that allows us to develop in isolation free from external threats. The Milky Way is more than enough. It is a closed system, yes, but it is a closed system containing near infinite possibility. And if the current inventory of the Milky Way is somehow insufficient for our ambition, patience offers a spectacular reward. We do not need to go to Andromeda because Andromeda is coming to us. In approximately 4 billion years, gravity will win its tug of war against cosmic expansion, pulling our two galaxies into a chaotic, beautiful embrace.